So let's take a brief look at the acidity of a terminal alkyne. So first of all, let's take a look at that word terminal. So that's when your alkyne, your carbon-carbon triple bond comes at the end of the carbon chain. When that happens, you're going to have a hydrogen bonded to one of your sp hybridized carbon atoms. The alternative is an internal alkyne where this is not possible. But it turns out when you've got one of these terminal alkynes, that hydrogen bonded to the sp carbon is more acidic than a typical alkene or alkane. So alkenes and alkanes have pKa's of like 44 and 50 respectively in most cases, whereas here the pKa is somewhere right around 25, 26. And in this case then, it has a chance of potentially being deprotonated. We might be able to pull off a proton transfer. Now it turns out it's going to take a really strong base still, but it is possible. And by really strong base, it turns out NaOH is not going to be strong enough. Notice if we used NaOH, the hydroxide would deprotonate that hydrogen and we would form water. But water has a pKa of somewhere in the ballpark of like 15, like 15.4 to be exact. And with the terminal alkyne having pKa of like 25, the equilibrium is going to lie heavily to the left and essentially to the point where this reaction doesn't largely happen. So NaOH is not really going to deprotonate a terminal alkyne to any significant extent. We've got to use a new and improved strong base. That's your classic Gen Chem strong base. Well, our new and improved even stronger base by a significant amount is sodium amide here, NaNH2. Now technically, sometimes you'll see this written as NaNH2 in liquid ammonia. Sometimes you'll see they just leave the liquid ammonia out. It's just the solvent. Whether it's there or not, it is the same thing. And in this case, though, that is a strong enough base to deprotonate this essentially 100%, or at least really close to 100%. And if you notice now, the conjugate acid you form from the amide ion is ammonia, whose pKa is 38. Compare that to the pKa of a terminal alkyne of 25, and our higher pKa represents the weaker acid, and so the equilibrium is going to lie towards the right here, and significantly towards the right, where again, essentially for all practical purposes, this deprotonates that terminal alkyne 100%. And the conjugate base here of our alkyne here, we call an acetylide ion. And we'll find out towards the end of this chapter that this is a very significant reaction when it comes to synthesis, because this acetylide is a great carbon nucleophile. And we have a chance of making new carbon-carbon bonds, which is pretty significant. But again, we'll visit that at the end of this chapter.